In this work, we present an approach to visualize multiple time-dependent scalar fields defined on 3D surfaces. Such fields describe different forces or quantities of scientific processes modeled by computer-aided simulations. Depending on the application, domain experts are interested whether there are correlations between multiple scalar attributes. The visual exploration of the complex data is mentally exhausting using standard visualization techniques. Therefore, we introduce a novel Skyline Visualization to easily explore the temporal behavior of multiple scalar fields simultaneously. To generate the Skyline Visualization, the surface mesh is first parameterized. We propose 3 ways to perform this. If only a small part of the surface should be flattened, the user can brush this region on the 3D surface. Here, a region with a low wall thickness on a cerebral aneurysm is brushed. Afterwards, this area is mapped to the 2D domain. To select larger surface regions, the user selects points which are connected to a cut line. Then, the user selects which of the separated regions should be parameterized. Here, the entire aneurysm should be flattened. The last option is for the case the entire surface mesh should be flattened. The user has to define a line where the mesh is cut open and which determines the border of the surface. Here you can see a lever surface where again cut points are placed to open the mesh. Afterwards, the whole surface is flattened, where for all 3 options the border of the resulting map is color-coded in 3D. Based on a 2D map, the 2D Skyline Visualization is generated. For this purpose, the map is sampled regularly. Each vertex on the map is assigned to a grid cell. Based on a focus grid cell, the surrounding grid cells are numbered clockwise, cut and ordered according to their number, which results in an unfolded representation of the numbers. To facilitate the understanding of the unfolding, the number-based topology of the grid cells is shown on the 2D map. Then, for each grid cell, a 2D skyscraper is created. They are divided into floors, where each floor represents a point in time. In addition, the scalar attributes are color-coded on the sides of the floors. To explore the data, a threshold can be set for each scalar field. If the corresponding median value of the nodes within a grid cell exceeds the threshold, the side of the floor is colored. In addition, the user can decide whether the value should exceed or fall below the threshold. Besides the solid color that indicates that the scalar field exceeds a threshold, the user can also activate a single hue color map for each scalar field. Furthermore, the user has the possibility to reduce the number of attributes shown in the visualization by selecting a subset of attributes which are then used to update the coloring of the floors. Similar to this, the color-coded value range of each attribute can be restricted. Since the 2D skyline does not show whether filtered bars represent continuous regions on the map or individual outliers, we also provide a 3D skyline depiction. This shows spatial relationships between bars. For each grid cell, a 3D bar is drawn on the map, where the division into floors is the same as for the 2D bars. To support the identification of homogeneous and inhomogeneous surface regions, the 3D skyscrapers can be connected by bridges, filling the space between 2 floors of adjacent bars. A bridge between 2 floors is only rendered if the same scalar fields exceed the thresholds. Moreover, the user can select a new focus point used to unfold the grid cells. With this, the homogeneity of specific regions can also be explored in the 2D skyline representation. By default, the grid cells are unfolded spirally. Depending on the application, it can be better to unfold them row by row. Here you can see the end-user dataset, which was unfolded by this scheme. With this, the user can better observe the reduction of the air volume fraction near the end-user. In addition, the highlighting of the current time step was activated in the Skyline visualizations. Unfortunately, surface distortions caused by the flattening are unavoidable. To reduce this problem, we integrated an interactive lens that is based on the idea of a magnifying glass. Thus, the user can enlarge distorted regions on a 2D map. Here, regions in the middle of the map are enlarged, where the user can control the width of the lens and its distance to the map. In the enlarged region, more skyscrapers are generated afterwards, which allows a more detailed exploration of small regions. The 3D bars are drawn on the map, where the sampling rate can be adapted by the user. However, occlusions may arise between the 3D bars. Therefore, we present different strategies to avoid occlusion problems. First, bars can be selected within the 2D skyline visualization, where only the corresponding 3D skyscrapers are shown on the map. The remaining bars are discarded. This reduces the visual complexity and enables a fast selection of interesting regions. Another option to reduce occlusion is the transparency modulation on the 3D bars. Therefore, we optimize the transparency based on the bar's importance. Bars containing more floors where scalar fields exceed the thresholds are more important than other bars. Here in the center of the map, a small region exceeds all thresholds, which becomes visible due to the transparency adaptation. The next option to avoid occlusion is to set a focus region in the shape of a cylinder. The user can activate the cylinder, translate it, and change its radius. Bars outside the cylinder are visualized in two selectable ways. The first option is that the bars outside the cylinder disappear completely, where the radius of the bars within the cylinder is adapted depending on the distance to its center. Bars close to the cylinder midpoint becomes wider. The second option is that also the bars outside change their size depending on the distance to the cylinder. To allow an efficient analysis, a linking between all views is needed. The user has the possibility to select an individual floor within the skyline, and the camera rotates automatically to the corresponding position on the 3D surface in a smooth way. Moreover, statistical diagrams are activated for each scalar field over time that show the mean value of the selected region. At the final position, a landmark is placed, where the user can enter an individual label. A list shows all placed landmarks with the corresponding color, where landmarks can also be reselected for exploration. Moreover, there is a connection from 3D to the skyline visualizations. The user can brush on a 3D surface, where only the bars are shown that represent the brushed area, which are also highlighted in the 2D skyline. At the end of the exploration process, the user can automatically generate a report summarizing all relevant aspects of the dataset for documentation and communication. It comprises four main parts. The first part presents general information about the dataset. In addition, renderings of the whole surface mesh from different perspectives are included. The second part summarizes the temporal behavior of scalar fields. It begins with an enumeration of the available scalar fields. Then, for each scalar field, some statistical values over all time steps are presented in a table. The third part provides an overview of the scalar distribution within the region, which was selected for parameterization. Similar to the first part, renderings of the selected 3D surface part are included. Moreover, renderings of the skyline visualizations are shown. Furthermore, for each scalar field, statistical information of vertices within the selected region are shown. The last part summarizes the user-selected landmarks. For each landmark, the temporal position and the user-defined label is listed. Moreover, the statistical diagrams of each scalar field at the corresponding position on the surface are shown. In addition, renderings of the landmarks are provided, where the scalar fields are color-coded on the 3D surface.